Hi everybody, sorry for being late. I was giving another talk, and then as always it was running a little bit longer. So I'm just gonna share my screen straight away, and I'm gonna start my presentation, and then I'm just gonna take 5 minutes break to drink some water and stretch my legs a little bit. Hope that you're all good. I'm sorry about sorry about the delay. And okay, recording is there. We're gonna pause that for the moment. Resume this, share screen once again. Okay, hello everybody. And yeah, so I apologize a little bit to the people who already attended the talk previously. You might hear some things again, hopefully not so much. So once again, if you have any questions, feel free to write them in the Zoom group chat. Or just interrupt me if you feel easier like that. So basically today we're gonna talk, why is this happening? So today we're gonna talk about basically ways to obtain these fits here on the right-hand side. So here you see the observations in red, the fit in blue. There is some way that I obtained this fit. So I was fitting some model to some data. And we know about models, we know about data, we had even hands-on on inference and on error estimation and all these things. So let's just see how is that put in the fully consistent way in the context of spectropolarimetric inversions. And this will be a little bit shorter class, I think, at least, depending on your questions and your participation, because first of all, I'm a little bit tired from already talking for 1 hour. The other thing is that I'm also a little bit disorganized these days. And finally, I want to leave some time at the end to answer some of your questions regarding homework, in case of if you all were wondering about some things and you were shy to ask. So let's get slowly into this. The goal of this lecture is to basically, well, let's say invert all that we were talking about. So we were talking about models, we were talking about physical processes, we were talking about line formation, what equations enter there, what problems we have there. Now we need to reverse engineer all these things to go from the spectra to the model parameters, right? And we also had actually 2 classes, one theoretical, one hands-on, where we really spoke about model fitting and inference and so on, not even connected to solar spectropolarimetry and so on. And we know that once we choose our model, and once we have our observables, and when we know what our model parameters are, we can perform some sort of inference. And in principle, that inference should be posterior maximization. So we are looking for the maximum, or ideally we are looking to sample the probability of individual parameter values given our observations. And we know that in the case where we have the so-called uniform priors, which means that all the parameter models are equally probable a priori, then this reduces to something called maximum likelihood. And this is, you see this maximum likelihood everywhere, right? And basically maximum likelihood under the assumption of Gaussian errors reduces to this chi-squared minimization, and chi-squared is this value which for Stokes parameters would look something like this. So take some time to, digest this. So what does this equation say? It says that chi-square, which is some measure of agreement between observed and synthetic, and by this synthetic you can say guess, you can say optimal, you can say whatever, fitted, whatever parameters, observables, is so chi-square is the sum over all, and here I'm basically separating my measured points into different wavelength points denoted by different i's, and 4 different Stokes parameters denoted by s, where I'm summing their differences, squaring them, and dividing by the square of the noise. And we talked about noise on Thursday, or the previous Thursday for the students from Boulder, where we saw how to estimate noise. And in principle, we assumed one number for the noise. Strictly speaking, noise should be different for different Stokes parameters because of different polarimetric efficiencies. and should be different for different wavelengths, because different wavelengths have different number of counts, which reduces in different scatter, right? So this chi-square, you usually write it down as a number, and you don't think about what this is, but chi-square is a function of your model parameters. And when we talked previously about the weak field approximation, we were fitting something with a linear dependency, and we said, well, in that linear dependency, my chi-square, or my posterior, or whatever you prefer, is the function of two variables. If you were in the previous talk, you already saw that. If not, I will repeat it. And actually, let's go to that equation straight away. Here, my synthetic intensity is function of 7 functions. Okay. So this is basically a very abstract way of showing radiative transfer process, and this is now intensity for different Stokes parameters for different wavelengths is a functional, which is basically operator, and this operator is all my radiative transfer process, all the hands-on exercise that we did on previous Tuesday, and so on and so on. All these things which connect temperatures, velocities, magnetic fields, everything in one functional, right? And what I'm trying to do is I'm trying to infer these functions. So how is my temperature changing with height? How is my gas pressure changing with height? And so on and so on. And this is, you are already guessing that this is very hard, right? Okay, and this is why basically this chi-square is a function of all these functions. So it's a very complicated story, right? And we're going to try and simplify this problem so that it looks at least a little bit more like something that we are used to. Okay, so if you want to do inversions, if you want to do this inference, there are many approaches, and since the goal of this is to prepare you for DKIST, maybe you will want to do things yourself. Maybe you will want to use something very simple, like the weak field approximation that we did previous class. Maybe something more, sophisticated, like something called Milne-Eddington approximation that you will try to do in the homework that you're going to get this weekend. Or you will want to use more sophisticated inversion methods, which means that you will really look for depth dependence of all these physical quantities. So strictly, this is a most general thing. Obviously, you can make some assumptions to simplify this. Like in our weak field approximation, we made assumption that magnetic field is not function of height, but is instead a constant, right? And that simplified situation a lot. You would do something similar for this Milne-Eddington approximation, for example, where you would assume that most of the things are constant except the source function that is linearly decreasing or increasing with height. However, in the most general problems that I want to talk about today is that, and I'm not going to talk about non-LTE, I'm going to talk about the generic local thermodynamic equilibrium case, which means Saha equation, Boltzmann equation, and the things like that. Is still the problem is still very complicated because we are talking about the depth dependence of physical parameters, and strictly speaking, we're talking about the functions and not fixed quantities. You can make your life even more complicated. You can take into account various fancy effects in your non-LTE calculations, such as something called partial frequency redistribution, which makes all problem even more complicated. Or you might even be the kind of your scientific question might be making a okay, your scientific question might need interpretation of some other spectral lines which are formed not really in the atmospheres but in something more looking like a slab or something like that, which is, for example, case if you're looking at prominences or filaments or something like that, right? And maybe Steve in his lectures will touch on these topics. Okay, so we are going to focus on these middle two. Actually, we're going to be focusing on the first one. So we have the observed spectra. We have measured it. We know all the physics. We have talked about physics. We want to know the atmospheric structure, but atmospheric structure is, strictly speaking, some continuous function. So easiest thing to do is to discretize, right? To divide my atmosphere is in many small, thin layers. And then I can use all these methods that we have already used to solve the forward problem and to calculate the line shape. And we did it together, right? And you sort of have a feeling for that. I gave you the atmospheric model. We were able to calculate all the needed quantities and to obtain something from that. And all this process and basically everything that we did is illustrated here. So this is sort of a flow chart how the line synthesis should look like. And this is something that I was showing you before, but I think now you can fully appreciate this, right? So if we start from the atmospheric model, which means we basically have a table with quantities of temperatures, densities, velocities, magnetic fields, we can use some laws of statistical physics, such as Saha equation and Boltzmann equation, to calculate what are the level populations of all the relevant things that we need. In our exercise, for example, these were the populations of the second and the third level of neutral hydrogen, right? Then from there, and from various assumed properties of our line broadening and so on, you remember that our line was looking very differently when we used Gaussian broadening and when we used Voigt broadening. We can calculate for each of the wavelength and for each of the depths opacity and emissivity everywhere, right? And then we can plug this into radiative transfer equation and get the spectrum. And here in this specific example here, I did that not for 1 atmosphere, but for 288 times 288 atmospheres, and I have obtained these synthetic spectra for each of the points. And now what you see here is that you see that in the higher panels, you have photospheric distributions of temperature on the left and velocity on the right. And these are simulated, of course, but they look a lot like the real sun, right? You see the intergranules, granules, you see velocities there, they make sense. And then when I look at the spectra there, this spectra carries some information about these pixels, but that information, the shape of the spectra is not determined only by the physical quantities at these levels. It's also determined by the physical quantities at other levels, and physical quantities at other levels could have significantly different distributions, right? So my spectral lines, as they are formed, they're picking up information along depth. And it's our job today to decipher that information, right? And the simplest way to do this is to do some sort of and you shouldn't really pay attention to this. There is another thing. There is a factor missing in this equation here. I just noticed. So the easiest thing to do this is to say, well, I have this. You know, now all these functions here are becoming some sort of arrays, are becoming some big number of unknowns that I'm generically going to call P, and this is my P in this equation here. So now what I can do is I can write some sort of a linear system which says, well, I started from some model. That model produces some synthetic intensity I synth here. That I synth is not exactly the same as my observed intensity. There is some discrepancy there, which I'm calling delta ISI. That discrepancy exists because there is a difference between my model atmosphere and the true model atmosphere. We know now that there is no thing as true model atmosphere, and even if there is, we can't know it. What we can know is the most probable model atmosphere given our model, right? Given our, when I say model, I mean generative model, given our physics that we chose. So the way to write this discrepancy here is to say, well, I'm going to write it as sum over all the model parameters. And here, model parameters mean mean all the values of temperature, magnetic field, velocity, and so on and so on. And I can write it sum over all these of the partial derivative of the synthetic intensity, which I have explicitly stated here depends on all the parameters, with respect of each individual parameter here, times, and what is missing here is the delta Pj, which means times some unknown modification that I need to determine, right? From the difference between my observed and my synthetic intensity. Okay? And this partial derivative here So this partial derivative of the outgoing intensity for different Stokes components at different wavelengths with respect to individual physical parameters at different depths is called the response function. And we have seen them before, and we're going to see a few more of them today. And I want to spend some time talking about these because I have shown them to you, and I have told you that response functions are very important because they show how your outgoing intensity is sensitive to blah, 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 which I'm saying now in a mocking way because I said it many times and it was not maybe clear why it's so needed. But the real reason why response functions are important is because these are really the partial derivatives of the outgoing intensity to our model parameters. And thanks to these partial derivatives, we can do fitting. We can perform our inference. And important response function, an important aspect of the response function is that it's really, instead of giving you some vague idea where your line is formed and so on, it's really telling you, if I perturb temperature at such and this depth point by this amount, my intensity is going to change by this much. It gives me exact number in units of intensity per Kelvin. And I can plug that into some sort of minimization procedure or fitting procedure and use that to extract real numbers and obtain agreement between observed spectrum and synthetic spectrum. And that's a big deal. That's important thing, okay? So let's discuss a little bit further what we see on this density plot here. So on the x-axis, we see the wavelengths. On the y-axis, we see the depths, and the intensity of the color is the intensity of the what I call response. So higher the stronger the color, more strong is the response. And this makes sense because these are, of course, the super beautiful, the spectral lines. And you see that in the line cores, we are sensitive to higher regions than in the continuum. And the continuum is very bland, very same everywhere. As we go toward the cores of the lines, our sensitivity is moving upward. And this basically tells us, okay, if I change the temperature in the photosphere at the level 0, what's going to change is the continuum radiation. The core will stay unchanged. If I change the temperature at log tau -3, my cores are going to change, but the left line is going to change more, the right line is going to change less. And we can connect that to the strength of the lines, right? The left line is stronger, it's formed higher, it's more sensitive to this region than the right line. And another difference of these so-called response functions with what you might use otherwise, which are, let's say, contribution functions or the log tau equals 1 depths or so, log tau equals 0 depths or so on and so on, is that response functions discriminate between different Stokes parameters and different physical parameters. So I can plot the Stokes function to magnetic field. I can plot the response function for the magnetic field for each of the Stokes parameters separate. So now what you're looking at is you're looking at the response of these two spectral lines to the magnetic field magnitude, and not only of the Stokes I, as I have shown you before, but also the Stokes V, Q, and U. And these tell you something about, like when you look at them like this, you will say, oh, well, this tells us that, a red line of, the 6302.5 is more sensitive to the magnetic field than the left one, which makes sense because its lambda factor is larger. But it will also tell us which wavelengths are more are sensitive to which depths in the magnetic field. So again, if I change the magnetic field around log tau equals minus 0.5 or -1, my wings are going to change, right? But if I change it at log tau -3, my core and my, let's say, inner wings are going to change, right? And in practice, these things that I'm showing here are matrices, right? I'm basically just visualizing some matrices here. And we're going to use now these matrices in a some sort of minimization approach to understand what is happening. So what I want you to remember here and to pay attention here is that these functions are beautiful to look at, and you can, you know, you're usually going to use them at some point in your life. You will be like, oh, well, it would be really cool if I put these response functions in my paper to illustrate which regions these lines are sensitive to, and so on and so on. And of course, there's nothing wrong with that. These things are very informative and very useful, and sometimes you see some very interesting things. But these response functions also have very real, very practical application, and that is that we can use them to devise inversion methods, fitting methods that fit a model atmosphere to the observed Stokes spectra in order to get maximum likelihood estimation of our model atmosphere. And that's something that is very powerful. And that's something which you will want to use if you want to extract some physical quantities from your observations, like, for example, strength of the magnetic field, orientation of the magnetic field, gradient of the velocity, temperature, and so on and so on. Okay, so how do we do this? So now we're going to talk about how we do this, and what are the steps, and what are some intricacies, and so on and so on. And a lot of these things are going to be very technical, and I don't think that you have to know all these things. I think it's good that you see them once. They won't be in any homework or anything like that, but I think it's good to maybe try and get you closer to this, and, you know, maybe demystify this process a little bit. Okay. So usually what we want to do is we want to minimize this discrepancy here between the observed spectrum and the synthetic spectrum. And the method of choice today for that is something called Levenberg-Marquardt minimization scheme. And once again, I swallowed delta Pj here, but luckily not in the second equation, not in the middle part of the equation here. So what I can write is I can say, well, discrepancy between the observed and the synthetic spectra at wavelength point I, and I have absorbed S into I, so basically I is now counting overall Stokes parameters and overall wavelengths, is equal to the sum overall physical parameters of the model of the response function times this perturbation delta Pj. And then the minimization scheme works like this. We start from a model atmosphere, which means a big vector with all the values of temperature, magnetic field, velocity at all the depths, and we calculate the emergent intensity, and then we estimate this, then we calculate these response functions, and then we see what's the difference between our observed spectrum and calculated spectrum. If they agree perfectly, which is of course never the case, we say, wow, amazing, we guessed the model atmosphere, let's move to the next pixel. Usually we don't manage to do that, so what we're gonna do is we're gonna solve this linear system here, right? So J is now my response function, delta Pj are my unknown corrections to the model parameters, and delta I are my known discrepancies between the observed spectra and calculated one. I can solve this linear system, which is never square, because usually I'm trying to have more wavelengths than the unknown model parameters. So I can squarify it by multiplying with J transpose, and then I can solve it, and I can obtain the corrections for model parameters. Then I correct my model, I try again. If it works, if it converts, great. If not, I repeat, and so on and so on. It might be confusing. This process of repeating here might be confusing for you. Don't forget that this problem, that this functional here, or we can stick to this, this line formation model is nonlinear, right? So temperature, as I have tried to convince you on many occasions, enters your equations in many places, and enters in very nonlinear fashion, right? It influences, line broadening through the square root of T, then in the ionization and the excitation, it's e to the minus something something over T. It's very complicated. It's very tricky. It's very convoluted, this process. And there is a lot of steps that we need to go through to decipher this. So that's why this process here needs to be repeated. And that's why most of the inversion schemes are some iterative schemes. And of course, some of you might ask now, well, but why are you using that? Why don't you use a genetic algorithm, or why don't you use a downhill model or something like that you have maybe came across at some point? You could do that. So you could devise inversion schemes which don't use derivatives, and there's nothing wrong with that, except they're mostly going to be relatively slow. So people tried many things, and they came to the conclusion that if you can calculate these response functions at least somewhat efficiently, derivative-based minimization is the way to go. Okay? So you can digest this slide slowly, and so on and so on. And the main goal is that you don't have to go into details of this because you most likely won't need it. But the main idea to understand is that if I know my response functions, which tell me how my spectra responds in a way to various model parameters, then I can devise a scheme that does the fit. Okay. So now we're going to talk a little bit how we actually calculate these response functions. So as I have tried to convince you, and I think I have convinced you by now, is that the road between having value of temperature given and calculating the spectral line is a very long one, right? So we're gonna go step by step. We're gonna say, well, let's say I perturbed my temperature in one of these points. So remember the model atmosphere, the temperature is basically just an array of points, and let's say that I have changed one of them by some amount, by 100 Kelvin. So something small but still appreciable. How does my outgoing intensity change? Well, let's try and address that using some sort of analytical way, right? So generally, my intensity, and this is a very nice argument from Jose Carlos del Toro Iniesta's book, which I always like to show, and I think it's a nice thing that illustrates what we need to do to find the response functions. So in an unperturbed case, in my original atmosphere, my outgoing intensity was the solution of this first equation here, right? Now I have perturbed my atmosphere, which means my opacity and my emissivity have changed. And if I have only perturbed it in one point, then it means that my opacity and emissivity have been perturbed in one point. But then it means that also my intensity has changed. And then I can write this, let's say, first order perturbation equation. And this should be d of I plus delta I. I'm sorry. So there is a brackets missing here. Okay. And but it's still gonna, the radiative transfer equation is still gonna be valid, because radiative transfer equation just tells you how things are changing. So then I can subtract these two radiative transfer equations for the perturbed and the unperturbed atmosphere. And I'm gonna give you 2 minutes of silence to convince yourself that this last equation here really is valid. So just keep in mind that this is d of I plus delta I, and just see what comes up. So I'm going to be silent for a few minutes and give you a chance to breathe and to take a look at these equations in peace. Okay, minute and 20 seconds was enough. So in principle, if you just multiply all these terms in the second equation, you can cancel delta chi times delta I, because these are like a second order thing. And then you subtract these two equations, you're going to see that the perturbation of the intensity follows its own radiative transfer equation, which has the same opacity, chi, and it has the, let's say, modified emissivity, which depends on perturbation of the emissivity minus perturbation of the opacity. I'm pointing with my finger, you cannot see that. Perturbation of the opacity times the intensity. Right, and this sort of makes sense, right? Because let's say that if I somehow perturb my parameters, that both my opacity and emissivity increase. Well, in that case, the perturbation of my intensity is going to depend on the increase of emissivity minus some effect which accounts for, you know, the fact that now some intensity is being absorbed. So this was just to convince you that in order to see how my outgoing intensity, which is ultimately going to be the solution of these equations here, actually how the perturbation in my outgoing intensity, which is going to be solution of this equation here, depends on finding appropriate changes in the opacity and emissivity due to this perturbation. Right. And of course, now comes the time for my favorite slide. The answers for these responses are found here, right? And we won't write them down explicitly, but you can think about this now and the ways how these parameters are changed by changing the physical conditions in the atmosphere. And for example, if I was to change the velocity, then this line profile, which is a local quantity, which changes from point to point, in the point where I change velocity would move to left or the right. If I was, on the other hand, to change the temperature, then this line profile would broaden, but also my level populations would change, because we said that these are basically set by the temperature. And if we assume local thermodynamic equilibrium, and this is what I'm calling, so the changes in this line profile are what I call here in the next slide obvious changes. So when I ask you what is temperature doing to the line shapes, I bet that your first assumption will be your first instinct at least will be to say, oh, well, the temperature, it will broaden the line. Increasing the temperature will broaden the line shape. Or if I ask you what is the velocity doing to the lines, you will say, well, you know, it shifts the lines or something like that. However, there is also this not obvious dependency of the temperature, which is the influence the temperature has on the level populations. And the way to account for these is to basically go through Saha and Boltzmann equations that I'm listing here again, which basically tell you that ionization and excitation state of the gas depend on the temperature through some analytic functions, and that we can find, given the perturbation in temperature, I can find the discrepancy, the perturbation in these level populations here, right? So I can literally take an analytical derivative of the temperature with respect to temperature of the Boltzmann equation and see, for example, by how much given population of my level changes when my temperature changes. However, to get that, I also need to find the derivative of the Saha equation, which then again leads us to this problem before. And now you see why this is such a big deal, right? Because you have seen that just to solve the Saha equation for hydrogen atom, we ended up, and if you remember the hands-on, we ended up with the quadratic equation, which led us to electron densities. Now imagine finding the derivative of all this process. It's a big, big, big amount of work, but it can be done. And when you do that, you will be rewarded with the capability to calculate these powerful response functions. So the whole, let's say, flow chart or a recipe how to calculate the response functions would be something like that. You basically follow the same process of calculating the line shape, except you need to take the derivative of everything there. So instead of just solving the Saha equation and to find the ionization states and so on, you have to basically see how all that system is being responding to the temperature perturbation. So you will say, okay, well, instead of just saying my ionization, my number of let's say neutral hydrogen at this depth is 10 to the 16, you're also going to obtain another quantity which says, well, the response of my number density of the neutral hydrogen at this depth to temperature is going to be, I don't know, 10 to the 12 per Kelvin or something like that. I'm inventing the numbers, and so on and so on. Then you again move to the next step. You say, well, I used Boltzmann equation to solve the level populations. Now, if I change my temperature, what's going to happen? Well, this Boltzmann is going to change, right? Increasing the temperature will increase the population of the excited states. Decreasing the temperature will decrease the population of the excited states. So then again, I need to find the derivative of the Boltzmann equation. Then, if you remember, the next step was to calculate the opacity and emissivity, right? So for that, we now need to take into account more than temperature. Temperature and density and the changes there will influence your damping. Line of sight velocity will influence your line shifts. Temperature and microturbulence will influence your line broadening. Magnetic field vector will influence the splitting and the polarization. And now putting them all together, there is a sentence missing there. So putting them all together, you will obtain the opacity and emissivity perturbations. And in most general cases, these opacity and emissivity perturbations will be polarized, and you will be able to calculate and to, so as I call it, propagate them. And by propagate, I mean solve this equation here to get the response functions, to get things like that. And important thing is that you will have to do this for each depth, because you will have, okay, if I perturb depth log tau equals 0, I'm going to get one value of my delta I here. If I perturb now at log tau equals -1, I'm going to get another one. So you will slowly, step by step, build these things here that you're going to use for your fitting, right? And that's a lot of work. That's cumbersome but necessary thing to do, right? And so now, after you get all these things, or you simply get the code from somebody that does all these things, to accumulate all these things, you might want to ask, well, okay, Ivan, good. Now I calculated all these things. I put them in this Levenberg-Marquardt technique that you told me about. It is super awesome. We're done, right? No, we're not done. That's actually, if you just apply it straight away, it's not going to work. And the reason for that is that this problem that we are solving is very degenerate and very poorly constrained. And to convince you of that, I'm going to show you, we're going to try, and we're going to do spectropolarimetric inversion. So fully depth dependent, very consistent, of one very, very simple example. So let's get on to it. This here, what I'm showing you, is a very, very simple line formation problem. So what we have on the upper panel is the source function that is decreasing from the deeper layers, which are on the right, toward the higher layers, which are on the left. By now, and I'm assuming some sort of line profile, and you know by now that this stratification of the source function, which is decreasing, results in some shape of the spectral line, and this here is the shape. And now we have done this together, and I definitely recommend you to go and study the line formation slides and the line formation exercise. We have sort of seen that once I give you the log tau grid at each of the wavelengths, and I give you the source function, that you can calculate the outgoing intensity. And the simplest possible relation between them is something linear, right? So there is, for each wavelength, there is some set of weights where I basically combine my source functions at all the depths to obtain the outgoing intensity, right? So all my, now in this deceivingly simple panel here, all my radiative transfer is hiding in these weights here. And I have shown you that basically these weights can be calculated in a very simple way, right? If you remember, in our exercise, we assumed that each of the slabs was completely constant, and that the solution there was very, very simple solution for the constant slab. And we were able to, calculate the outgoing intensity, and that looked really, really nice, and we were quite happy. Okay, maybe we're not quite happy, but we sort of understood how the lines are being formed. Now we are solving the inverse problem. So now we are pretending that this spectra here is the observed spectra, and that our source function here is the unknown quantity. And for the simplicity, I'm going to assume that these weights here, which basically depend on my line profile and on my optical depth grid, are known, right? So in a way, I'm simplifying the solution of the radiative transfer equation that you see up here. I'm simplifying it to some linear combination of the source functions, and it's actually not so bad approximation. So what I want you to see here now is that this is again a linear problem. So my outgoing intensity at different depths is the sum over all, at different valencies, sum over all depths of the source function weighted with some wavelength dependent coefficients. I know the coefficients, I know the intensities, I want to find the source function. It should be super simple. And so far, this method has never failed us, right? We try to do the deconvolution using that, we try to do the demodulation using that, it worked great. So it must work great here, right? This is so simple. It doesn't work. So here in blue, you see the original source function, and here in orange, you see what is the solution of this linear system. So this is, once again, this linear system is super, super simple. Toy model, line formation, that I'm just using to illustrate the radiative transfer problem. In practice, this is much more complicated. There are many things influencing the solution of this integral and so on and so on. But even for super simplified problem, I'm getting this oscillatory behavior. Why is this so? Does anybody have an idea? You can write in the chat if you want. Somebody had an idea and then changed their mind. Go ahead. Ill-posed numerical problem because of the degeneracies. Exactly. Yeah. So this linear problem here, thank you for the input. That's exactly true. This linear point here, this linear system here, is something that we call ill-posed. And ill-posed, the easiest way to understand this is to say that rows of this linear system are very similar to each other. So you might write, in general, you think like, yeah, okay, if I have a linear system which has more rows than columns, which means it has more measurements than the unknowns, I can solve it and it's going to be great. However, that's only true if all these measurements are independent. So obviously, if I give you a linear system which says x plus y is equal 0 and x minus y is equal 2, you can solve it, right? However, if I tell you x plus y is equal 0 and 2x plus 2y is equal 0, it doesn't mean anything because it's one and the same equation, just multiplied by 2. Now, these were two extreme cases, two independent equations and two completely dependent equations. In these situations, sometimes what happens is that your linear system is poorly determined or ill-posed, which means that the equations are very, very similar. So when I try to invert my matrix, my numerical imprecisions and so on eat my solution. And this is actually a very nice example here. What can appear is we can get much more. In the general case, when we have all the dependencies and everything is nonlinear, this can be much worse than this. Which in principle means that I cannot infer any arbitrary fine distribution of my physical parameters, right? The reasons for that are multiple ones. If you go back and look at the response function, you can see that some depth points are simply not important. And in the other case, there are other things that are simply, very degenerate. So for example, the response function for the left line at minus 2.6, I don't know what is this, and then minus 2.8 is very similar, right? So it's simply, if I change one point by a certain amount and the other one at the same amount just with the opposite sign, there might not be any difference in the end. And people, I apologize for people who are seeing this again, another way to convince yourself of that is to look, for example, at how complex your observations are. And here I'm looking at the set of observations of sodium D lines. And what we have here is that if we do something called PCA decomposition, which basically tells you how many eigenvectors, which means orthogonal basis vectors, you need to describe these spectra, instead of thousands, which would correspond to number of valence points, what we actually see here is that it's more like tens. So there is not so many independent information in our data as we might think. And that is why we use something called nodes. And the nodes are, and when you start doing inversions and talking with people who are doing inversions, you're going to be hearing about these nodes all the time. Nodes are a way for us to simplify either the atmosphere or the corrections done to the atmosphere. So what I'm showing you here on these panels is a fully stratified atmosphere that is being perturbed by some amount, but instead of perturbing each depth point separately, I only have 5 predetermined positions where I'm allowed to do the perturbation, and the perturbations in behind have to follow these perturbations in green points according to some method that we have agreed. Either it's a spline or a polynomial or something like that. So what we have here basically is that we have simplified our fully stratified unknown temperature stratification to only 5 parameters. Okay? So instead of having, I don't know, 50 or 100 points for my depth-dependent temperature, I now only have 5. The same thing is for the magnetic field here on the right. Instead of having 50 or 100, I have 3, so on and so on. And these nodes are basically now sort of a map that they allow us to find a map that sort of simplifies our model. Instead of having these, 50 points for the temperature, 50 for the magnetic field, 50 for the velocity, I have few for the temperature, few for the magnetic field, few for the velocity. And since I know how changing these nodes creates the change in my atmosphere, I can do something like this. I can write now, and this is a bit more abstract, but if you are into this, take a look at this. It helps you understand stuff. Now what I have is, now I have these alpha values, which are the values of my parameters, which are my nodes, which are denoted here by the red points, which determine my values of P, which are my depth-dependent values, which are blue lines. And I can calculate the response function to the node values by basically summing over depth the original response function, which was depth-dependent, times the response of the depth-dependent quantity to the node value. If you're not into this, don't feel stressed. This is something that is not obligatory to know, but this just helps you understand how the inversion method is devised. Because after that, what I'm going to end up with, I'm going to end up with the derivatives of my observable to my model parameters, which are actually nodes. And instead of having hundreds of them, I'm going to have 10 of them, 20 of them, 30 of them. And then I can use more reasonable fitting techniques to infer this. Okay? And then we can devise these nice GIFs and inversions and things like that, where in the left 4 panels, so this is obviously a toy model, very, very simple. You see how the Stokes I, Q, U, and V are changing with iterations to fit the red line to the blue observations. And on the top right-hand side, you see how the temperature certification is changing. But even though the temperature certification here might have 50, might have 100, might have 500 points, the only variables that are actually being changed are the blue points, the nodes, and the green line in between is forced to follow the stratification of these nodes. And then on the bottom right, you see how the chi-square, which is the measure of the agreement between the blue lines and between the blue point and the red line, is decreasing with number of iterations as we are getting better and better fit. And this now works because now these 5 points are more independent. So here we were in a situation where many, many points describing my source function run with depth were not independent enough, so they were creating this numerical noise and this oscillation here. When I decrease that to only 5, now I'm able to fit even much more complicated line formation model. And what is actually happening here is that we are having some non-LTE line formation model. Okay? This is not something that is very well defined. There are no books on how to choose these nodes and how to mathematically prove that they're correct. This is something that is basically left to us, and that is why sometimes people say that in spectropolarimetric inversion is an art or something like that, and we always like to say that. I'm not proud to say that. Usually I'm very annoyed by the fact that there is not very well defined rigorous process how to treat that. Unfortunately, there is still, or fortunately, this means that there is still time that there is still space to explore and to learn and to progress, and we will probably come up with some better techniques. It would be very nice to have some feedback from people from other fields, showing them how are they doing their regularizations, because strictly speaking, this is a form of regularization. Regularization is a process when we have the unknown, which has a lot of free parameters, is ill-posed, so we impose some additional constraints on that to make it behave nicer. Here, my additional constraints were that I have only these 5 points. Okay.
Ivan?
Yeah.
So, just a quick question. When you're minimizing the chi-square, don't you have to stop when the normalized chi-square is about 1?
Come again? Do I need to normalize chi-square?
No, I'm saying like you have to stop the inversion of regularizing. Sorry, you have to stop the inversion when the reduced chi-square goes to 1, no?
I should, right. In principle, yeah. Okay, that is true, assuming that I know what my noise is, right?
Sure.
So don't pay attention to units here for chi-square. You are right. Yeah, if you know your noise and you're confident about your model, you should stop when chi-square reduced hits 1. You could stop. The thing is that you're looking for, in most of the inversions, you're looking for the maximum likelihood.
Mm-hmm.
So you really want to hit the minimum, because maybe you were wrong about your noise. Maybe you were wrong about your model. But in principle, what's going to happen here is most likely is that in practical examples, unless your noise is huge, you will never get even close to chi-square reduced equals to 1.
Okay.
There is this very nice paper, I have sent it to you in the email, which is called Do's and Don'ts of Reduced Chi-square. And there these authors basically show and tell that the basically chi-square reduced is only appropriate when you have a linear model and you're sure that your model is appropriate for the data. we know in spectropolarimetric inversions that in most cases our models are not appropriate. So we don't have all the opacity emissivity contributions. Our temperature and other certifications don't behave like these stupid polynomials, and so on and so on. So this, I think this hitting chi-square reduced to 1 is the least of our problems. But yeah, in principle, you're right.
Okay, thank you.
But
And these blue
when you're,
sorry,
Ivan, in this case, when you're regularizing, is there an iterative or Monte Carlo process that does that?
No.
So that it
Sadly, no.
does it automatically? Because from what I know from regularization techniques, you use a base guess and then you run it one more time. So it's quite fixed.
Yeah, here you choose at the beginning where these points are, and yeah, that's it. You can, you can change the position of these blue points to see if something does better or worse, but there is no really consistent way of adjusting the number of blue points and their position. I'm calling them blue points, the nodes and their position to get the best way. So I would really like to hear some more advanced way how this could be done. It would be great.
Yeah, but if you do it more advanced, you might get into issues like you're doing with Monte Carlos when you're overfitting.
Okay, I see.
I'm not sure, but
okay,
it sounds like that.
Okay, yeah, because I think it would be really great to put some rigor into this, because now we are basically left to either just say, I'm looking from here to here, put them evenly spaced between, or do some ad hoc solutions. We can discuss this in the meeting later or something like that. So now I have shown you this image before, and I have even shown it in the previous panel. So in the previous talk. So this is the reason why I'm always showing you maps at some weird predetermined optical depths. It's because these optical depths respond to position of my nodes in my inversions, and nodes are my actual model parameters. So what were K and N in the linear fit that we did last week and the week before that are now these node values, except they enter my model in a very nonlinear way. But these are the actual values that I'm obtaining, and so I can show you the maps of these values, okay? And of course, from these, I can reconstruct the fully stratified model atmospheres, but the question is whether these fully stratified model atmospheres make any sense. Okay. So to conclude, what does this mean for you? If you want to use a DKIST is spectropolarimetric instrument first and foremost, which means that you will have to probably deal with some sort of, I said inversions, maybe not inversions, but inference. Maybe you will do something simple yourself, big field approximation, Milne-Eddington, something like that. Maybe you will want to write your own inversion code or learn how to use one of the existing ones. I will put the list of the inversion codes and the reference papers in the lecture notes one of these days. Or maybe you will want to make use of our level 2 project and have us do the inversions for you. And in that case, what you will get is a model atmosphere for each of the spectra that you have observed, which means that in addition to getting the Stokes cube of the observed Stokes spectra, you will get another cube, which will be like X, Y, Z for each parameter, so that you can analyze that. However, whatever you end up using or not using, is good to know what physics come in there and what is the connection between your model atmosphere and your synthetic spectrum. And since this course can't pretend to teach you all these things, and there are also much more wide range efforts, which have now been, of course, paused because of this extraordinary situation we are in, but there is planned DKIST workshop dedicated solely to inversions, and more specifically Milne-Eddington inversions. It was supposed to be almost 3 days, and some of you applied for that. Unfortunately, we postponed it, but to my knowledge, it's still going to happen, so keep an eye for that. And there was a spectropolarimetry school, I think 2-week long, to take place in Boulder at late autumn, end of October. And there we will, I will also be teaching there, as well as many other much more experienced and much more senior colleagues. We will be tackling all these things in much more detail, and we will do much more practical things related to spectropolarimetry and the inversions. And I really, really hope that everything will be okay by then, and that's going to happen, because I think you would have amazing time and we would all have great fun working together. So keep an eye out for these things. Okay, so questions, comments?
Ivan, has anyone looked at the effect of changing the way you interpolate the nodes on the way you fit your spectra? Because that was also part of your model, right?
You're amazing. Yeah, that's amazing remark. Yeah.
So
Choice of how you connect these points is a part of the model. So obviously, if I connect them linearly and I connect them using spline, I'm going to get the same, I'm going to get different stratification of the atmosphere from the same nodes, which in turn means that to get the same similar enough stratification of the atmosphere, I'm going to have to use different nodes. I don't think that people tried to play with that too much. People just use what is well behaved. So you want to be sure that if you have all nodes between 8 and 4,000 Kelvin, you don't have some explosions or oscillations in between.
Okay.
Yeah, but that was a very good remark. The interpolation is the part of your model. So you settle on that at the beginning. More questions? Okay, then let's talk a little bit about your last homework and a little bit about the plan for the remainder of the course. So quite a few of you asked me about the first problem where you have to devise this. So let's actually open Valentin's slides so that I can show you this thing. So some of you asked this, I answered you, but maybe more of you had the questions. Let's see how the PPTX will work in my LibreOffice thingy. So the most of the questions were about this rotating wave plate and scheme there. The relevant slide in Valentin's lecture, and you can also find it in Introduction to Spectropolarimetry and probably other books and papers and things like that, but the relevant slide is 65, if I'm not mistaken. So if you go to the slide 65, yes, is this one. Okay, so the 65 shows you basically, oh no, my God, no, I want shift. Oh, but it doesn't work. Start from the current slide. Okay, so this is the relevant slide, which shows you the equation that you need to do the exercise is the last equation. So the last equation tells you what are you measuring for the given retardance delta, which is fixed. So the retardance is the property of your wave plate, right? It basically depends on the thickness. And we found, and we are settling on the retardance of 127 degrees. So first of all, keep in mind that Python wants radians. And then we are rotating the wave plate, and we are measuring Stokes parameters at 8 different positions. And the most of you had problem of choosing these positions. And the natural thing to do would be to say, well, I want 8 intervals from 0 to 2 pi. So I want 0, pi quarter, pi half, 3 pi quarter, pi, and so on and so on. However, keep in mind that in the equation itself, we have 2 omega t and 4 omega t. We never have omega t. So sampling from 0 to 2 pi doesn't make sense. We need to sample from 0 to pi. But then again, we want basically 8 different steps, and which according to we want 8 different steps, and we want Q, U, and V to enter in all of the equations. That's one of the assumptions of this modulation scheme, that Q, U, and V appear everywhere, right? Right, so see here, you can see from what you're supposed to get that Q, U, and V appear everywhere, which automatically means that I cannot have omega t, which in some of the equations appears as A. We cannot have it being equal to 0 because sine of 0 is 0, and V would not appear there. So we basically need 8 equidistantly spaced values on the interval from 0 to pi, which do not involve 0 and do not involve pi. So you should think a bit how to make that one. And keep in mind that periodicity of your problem is pi, not 2 pi. So I tried, I found it, it works, it gives the correct modulation matrix. So give yourself some time, try to work on that. And I'm pretty convinced that you can get it. If you cannot, no worries, just write to me and we'll settle that. It's not a big deal. The important thing is that you go through the exercise and think a little bit. Bonus points if somebody wants to show how to go from the first equations here back down to the other ones below. For that, you might want to go back and to read a little bit and so on and so on. Okay, so that was the problem with the first one. For the second one, there was a question how to simulate this seeing-induced polarization. I'm just going to remind you what the seeing-induced polarization is. So seeing-induced polarization is the effect where your image shifts between individual modulation, well, not cycles, but individual modulation measurements. So for example, if we were to look at this modulation scheme here, for the first row, I'm looking at one image, and then for the second row, my image shifts, let's say by some amount, or distorts or something like that. Really proper way to simulate this would be to apply, for example, different phase screens for different of the exposures. However, that's very complicated. You don't have to do that. In the class, we did that just by shifting the image by hand. So you can do something like that. But keep in mind that in the class, what I did was I plotted you maps of the polarization for individual valence. What I want you to do now is to focus on one point and to plot the wavelength dependent crosstalk. So this is what we call seeing induced crosstalk. Okay, and you might want to experiment a little bit, and if you remember, maybe this seeing induced polarization and seeing induced crosstalk are the strongest at the places where the spatial gradient of intensity is the highest. So I'm not going to give you more hints now, but keep this in mind, and if you have troubles, just write to me. There's going to be one more homework this weekend, and then probably one more after Masha and Steve are done, and that's it. There won't be anything else to do, and yeah, we just need to finish everything until the deadline for the marks is. So don't worry too much about the deadlines, but also try not to swamp me so that I have to grade you all the time last few days of the semester, although it's not the worst thing in the world either, because there is not much else that we are doing right now. Okay, any questions? Okay, in that case, our next guest lecture is going to be Masha Kazachenko. Masha Kazachenko is going to give 2 talks and 1 hands-on. So the first talk is on Thursday, then another one on Tuesday, and hands-on on another Thursday. It's still going to be hosted from my Zoom. So just come here at 2 as usual, and we're all going to enjoy the talk and chit-chat and so on. Okay, take care. I hope that you're all good. If you have any problems, if you need help with the homework, if you have any questions regarding anything, if you need somebody to chat about anything, feel free to get in touch, and stay safe.
Are we gonna have the journal club here?
Sure. Let me just stop the recording.